So here in this video, we look at what's known as the hydrohalogenation reaction, or as we often refer to it in class, just the HX addition. This is a reaction that's the addition of a hydrogen and a halogen to an alkene. And it happens in a Markovnikov fashion. And we'll review what Markovnikov means in a few minutes. So as to the history of this reaction, it's basically safe to say that this reaction's been around for a long time. And while it's not readily apparent who's the original discoverer of this reaction, citations on this reaction date back to at least 1869. And we know it goes earlier than that because those studies in 1869 were done by Markovnikov and looked at the regiochemistry of this reaction. How does the reaction work? What's the mechanism? Well, it's a basic two-step mechanism here. And in the first step, the alkene functions as a nucleophile, attacks the hydrogen of the acid, the HBr here, and kicks out the bromine. Now, in any case where the alkene we start with is not symmetric, such as this one, that gives us two possibilities. We can put the hydrogen on the first carbon of the alkene and the carbocation on the other carbon, or we can reverse that. From here, the bromide anion attacks the resulting carbocation. And as you can see from this compound, 1-propene, we have two possible products, 1-bromopropane and 2-bromopropane. But Markovnikov's rule provides us with a way to predict which of these products is preferred. Recall that Markovnikov's rule says that in an addition reaction to alkenes, the X group, which in this case is the halogen, will go to the more substituted carbon, and the hydrogen goes to the less substituted carbon. And so for this reaction, we would expect that as drawn over here on the right gives us our preferred product. Now, why is that the preferred product in this reaction? Well, what we want to look at here are the intermediates. The first intermediate is a primary carbocation, whereas the one that gives us the major product is actually a secondary carbocation. So we've learned previously that the more substituted a carbocation is, the more stable it is. But why does that help us with preference for a product or in a reaction? Well, this reaction, being a two-step mechanism, would have an energy diagram that looks like this. And this intermediate point here, that's our carbocation. So if we have a more stable carbocation, then that carbocation will be lower in energy. if that carbocation is lower in energy, then that maximum point will also be lower in energy. That maximum point being our transition state. Well, if the transition state is lower in energy, then that results in a lower activation energy and a reaction that takes place more easily. So these reactions will, in most cases, again, give the product that comes from the most stable intermediate. Now, how do we even know that this reaction goes through a carbocation? Because a carbocation is not something that you can actually see. They're unstable, so you can't isolate a carbocation. So how do we actually know that a carbocation is part of our reaction pathway? And so in this course, we don't really get into a lot of how mechanisms are determined. But we can talk about it a little bit in this case. So back in the early 1900s, a chemist by the name of Frank Whitmore was working on the HX addition to this alkene. And if this follows the same pattern that we've been looking at, then we know that the halogen will end up on the more substituted carbon. But what Whitmore found is that, surprisingly, the halogen actually ended up on this carbon, which is surprising because that carbon is not part of the original alkene. So how is it that the halogen ended up there? Well, if the initial alkene attacks the hydrogen, we form this secondary carbocation. But it turns out, and this is something that's been well studied, that if you have a situation like this one, this hydrogen here, if it takes its electrons and moves over a carbon, we now get an even more stable tertiary carbocation. And again, this is the kind of thing that really only can happen if it gets you a more stable carbocation, and almost always it has to happen on a neighboring carbon. But now that tertiary, that more stable carbocation, can lead to the product that Whitmore saw. And so, with the exception of a case like this, where we get something unusual happening, the addition of HX to an alkene will always give us the Markovnikov or the more substituted product. Is there ever a way to get the less substituted product? What if you wanted that halogen, that bromine or chlorine, on the other side of the alkene? So it turns out there is a way to do it. It's a reaction we'll talk about much, much later on in the course, but I will just mention it very briefly here. If you add still HBr or HX, but you do it in the presence of a peroxide. So peroxide being a compound that has an oxygen-oxygen bond in it. In that case, you can get what's known as the Antimarkovnikov product, or the product where the halogen ends up on the less substituted carbon. All right, let's just look at a couple of examples. So in this first example, our alkene is here. If it reacts on the carbon on the right, we'd get a primary cation, but the other carbon would be secondary. And so we get substitution on the more substituted carbon. The second example is a little bit more complicated. And the reason it's a little bit more complicated is both of these carbons are secondary. But if we look at the two possible carbocations, that should help us to distinguish which one will be preferred. Again, both are secondary. But in this top structure, this carbocation is also next to an aromatic ring. So it isn't just stabilized by being secondary, it's also resonance stabilized. And again, anything that helps to stabilize that carbocation is going to make it the preferred pathway. So what are some applications of this reaction? Again, not a lot of independent applications for this reaction. Most of them are synthetic because we don't see a lot of halogens in naturally occurring compounds because halogens are generally very reactive. But probably one of the most common applications is if you start with something like styrene, you form a carbocation here, which then could get attacked by another alkene. And that forms a new carbocation here, which can then get attacked by another alkene and continue on indefinitely. And so it turns out that HX addition can be a very useful way to initiate a polymerization reaction. Are there other functional groups that you want to be careful of when you run one of these reactions? The answer is most likely yes. Something like HBr or HCl, those are all strong acids. And so strong, especially these types of strong inorganic acids, are very, very reactive. And a lot of functional groups, especially things like alcohols, as well as some carbonyls, can also be affected by the use of strong acids like these. So if you're planning out a synthesis, those are some functional groups that you really want to watch out for. Again, carbonyls as well as alcohols, because strong acids like HBr and HCl will react with a large number of different functional groups.